Section 3.1, Absolute Extrema. So absolute maximums, or absolute minimums as well, absolute extrema, you can have an absolute maximum, f of c, that's the y value, is a maximum if that y value is greater than or equal to all the other y values for x in an interval. Please note, it says greater than or equal to. All right? So it could happen such that something like this it's greater than all the other y values in here, but it's also equal to this y value. So the maximum essentially happens twice, but there's only, even though it happens twice, there's only one maximum. Same thing for the minimum. If it's less than or equal to all the other y values for x in the interval. Now this does not specify whether it's an open interval or a closed interval. However, here's what the extreme value theorem says. If f is continuous on the closed interval from a to b, then f has an absolute maximum and an absolute minimum. Here's the key things here. Function's got to be continuous and a closed interval. Here's why that's important. If it's not continuous, it could be like this. Let's say we're going from a value here to b value here. This could be an, right here, an asymptote. So while it might have a minimum, it has no maximum because it's not continuous. It could also be like this. Here's A, here's B. It could go up, and then all of a sudden have a hole right there, and come down to right there. The maximum doesn't exist because it never actually reaches a single number. It's got to be a single number. It might be getting really, really close to, let's say this is 3, but there is no, it doesn't exist right there. Here's also why it has to be a closed interval. Can't be an open interval. Let me show you an example of an open interval. Right here. Here's A, here's B. Now this happens to have a maximum right there. But the minimum looks like it'd be right here at B, whatever that y value is. But because it never actually reaches that number, there is no minimum. So it has to be a closed interval. So here's some examples of ones that work. Here's A, here's B. So the maximum might be right here. That's the absolute maximum. This is close to this value, but it's not actually a minimum. That's what we call a relative minimum. That's a relative minimum. We often abbreviate like this, relative minimum. This, though, is the absolute minimum because it's lower, it's less than this one. And as I said before, it may happen twice. So if I got a closed interval here, here's A. I'll call it B. Here's A. It may happen more than once, and there's a minimum right there. Or it could come all the way down to here and come up. That would be the minimum then. So the big things to take away here, it's got to be a closed interval and the function has to be continuous. That's what happens. That's how we know there's an absolute maximum or minimum. Now, how can we actually find those numbers? Well, this is just an existence theorem. This just says if it's continuous on a closed interval, then it has an absolute maximum or minimum. That means an absolute maximum exists. So how do we find it? Well, let's look at some of these again here. Let's say we have a parabola right here. And let's say we've got an absolute value function right here. Here's A, here's B. Here's A, here's B. Let's look at when the absolute maximum can occur. On this one, the absolute maximum is obviously right here. Here or here. Either one of these 2 points. We could say it's the same point. You know what? Let's just change this and make it go. We'll say it goes up a little higher. Which do. And we'll say here's the B value right here. So absolute maximum is right here. And the minimum is right here. On this one, here's the absolute minimum. Here's the absolute maximum. So what do we notice about these here? Well, the minimum and the maximum can occur at the places where the extrema can occur. The endpoints. So we're going to have to check the endpoints on the closed interval. Have to check the y values for the endpoints. So we have to check f of A and f of B. That might be bigger than all the other numbers. Also, right here, we notice something else about these two. The derivative right here. What's the derivative right there? Give you a moment to think. The derivative right there was 0. It went from decreasing to increasing, and it changed right there. It changed from, the derivative there would be negative because the slope was going down, then all of a sudden positive. Not the slope was going down, the function was decreasing, and the function was increasing. The derivative is negative, then the derivative is positive. It switched right there, which means it was 0. Well, you say, Mr. Kuhne, what about right here? The derivative along here is going to be positive, then the derivative over here is going to be negative. But the derivative right here does not exist. You're correct. The other place to check is when f prime of x does not exist. Those are the 3 places where extrema can occur. The endpoints, anytime f prime of x is 0, or anytime f prime of x doesn't exist. So how are we going to check this? Pretty simple. We're going to find when f prime of x equals 0, when f prime of x does not exist, then we're going to check all those critical points and check the endpoints. This is the part that is the most difficult for students. You forget to check the endpoints. All right? You forget to check the endpoints. Critical points, I didn't get to this yet. Critical points are just when f prime of x is 0 or undefined. That's all it is. That's where extrema can occur. That doesn't mean they do occur there. They can occur. places where extrema can occur. It might be there, it might not. In fact, what can also happen is it may go up, be 0, and then keep going up. The derivative right here is 0. But it is not a maximum or a minimum. So that's why we also had to check the endpoints. Can't say it's enough. If you want to find an absolute maximum or minimum, you've got to find when there's 0, then you're going to check those and check the endpoints. So let's do one here. Find the extrema of 3x to the 4th minus 4x cubed over the interval -1 to 2. All right. First, find critical points. F prime of x. So the derivative of this is going to be 12x squared minus 12x cubed minus 12x squared. So I got to find when this is equal to 0 or undefined. It's never undefined, so we just got to find when it equals 0. Couple different ways we can do this. I could do it by hand, factor out a 12x squared. I'm going to get x minus 1 equals 0. So 12x squared equals 0, or x minus 1 equals 0. 0 and 1. Now, that worked out nicely, neatly. If you take the derivative though, and it doesn't give you a nice, pretty function, you may have to use your graphing calculator to do that. So, I even did that here. Took the derivative. I got to find when it is 0. Well, 0 right there. At 0. And it is 0 at 1, 0. So 2 places there. There and there. Just got to find where the function is equal to 0. On your graphing calculator, you have to take the derivative, graph it, and then you got to find when the derivative crosses the x-axis, also known as the zeros. All right. So maximums and minimums could occur here. These are possibilities. It's critical I check them. So now I'm going to check critical points and endpoints. X and f of x. So I'm going to check -1, 0, 1, and 2. I'm going to check these in my original function. So if I plug in -1 into my original function, -1 to the 4th is just 1 times 3. If -1 is, I get 3 minus -4 gives me 7. Plug in 0. No, that's easy. That's 0. F of 0 is 0. Plug in 1. Get -1. And plug in 2. That's going to be, let's see here, 1648. And then 2 cubed here is 8 minus 32 is 8. 4 is 32, and that's going to give me 16. So now I don't really care what's going on in between here. The maximum on this one, F has an absolute maximum. Sorry about that, Mrs. Kuhne called. All right, so F has an absolute maximum at f of 2, which is 16. So the maximum is 16. It happens at 2. Let's be a little more clear about this. At x equals 2, the maximum is 17. The max is 16. F has a minimum at x equals 1. The minimum is -1. All right. So, how do we check? Find the critical points and check the endpoints. So you're going to find the derivative, set it equal to 0. Okay, find all critical points there and there. If it's undefined, you have to include one of those points. There may be various reasons why it might be undefined. Then we got to find then all we have to do to find the maximum minimum is check all the endpoints and the critical points. That's all we have to do. This is surprisingly one of the more missed questions on the AP exam because of what we do later, where we use the first derivative test to tell something the maximum or minimum. But if it's a closed interval, if you're working on a finite amount of time, you have to check the endpoints. All right, that should do it. I'll try to find an example for tomorrow. Go ahead and work on your homework. Once again, it's got to be continuous on a closed interval for there to be an absolute maximum or minimum. It can happen more than once. And to check it, to place where extreme can occur, could be at the endpoints or the critical points. So we're going to find when the derivative is 0 undefined. We're going to use those critical points and check the endpoints in the original. And that will tell us the maximum minimum. Notice we're plugging into the original, not the end function. Thanks a lot. Bye.